Black holes. Are they really what we think they are? Science fiction movies have led us to believe that black holes are two-dimensional black warp holes that can transport people through time and space. This has not been proven. What we do know of black holes, however, is just as interesting. A black hole is what remains when a massive star dies. Stars are like fusion reactors made out of gas. The fusion reactions in the core are very much like a fusion bomb. The way that the black hole is formed from these massive stars is that the fusion reactions in the center stop as it burns up the gases. Then it starts to attract matter and compresses it with gravity. Then the compressed material heats and eventually creates a supernova explosion. The material and radiation blast out into space, while what remains is a massive compressed core whose gravity is so strong that even light can't escape. This object is now a black hole. Since the gravity traps light, the object seems to disappear as its surface doesn't emit or reflect any form of light. The black hole seen in sci-fi movies is usually a two-dimensional hole that sucks in everything around it. But the black hole some scientists theorize about is a sphere with a strong gravitational pull. It can even have satellites that don't get sucked into its core. The center of the hole is known as the singularity, while the opening is called the event horizon. There are two types of black holes: Schwarzschild, non-rotating black hole, and Kerr, rotating black hole. The Schwarzschild is the simplest, and it's the one that has only the singularity in the event horizon. The Kerr rotates as the star it came from rotated. It contains two extra parts than the Schwarzschild black hole. In addition to the singularity and the event horizon, Kerr black holes have ergosphere, an egg-shaped area of warped space around the event horizon, and the static limit, or the place between the ergosphere and normal space. There are a couple things we can measure about black holes: mass, electric charge, and rate of rotation, or angular momentum. In other words, the rate at which the black hole is moving as it rotates. Mass is what we can measure most reliably due to systems like binary stars. Binary stars are stars that orbit around each other. When we see a star that's orbiting, but we can't see what it's orbiting around, we can assume that what it is orbiting with is a black hole. The concept of a black hole first originated in the late 1700s. A scientist at the time, named Mitchell, calculated that if a star was 500 times the size of our Sun and had the same mass, the escape velocity, or the speed needed to escape being pulled toward the planet, would exceed the speed of light and therefore could keep light from escaping to its surface. There's a lot of controversy about this, as people couldn't believe that light was affected by gravity. Then, in 1915, Albert Einstein introduced his general theory. It was a theory of gravitation and its effect on light. In this theory, he states that matter causes space-time to curve, and this curve is what light follows. So if the path is curved, then light could be trapped by a black hole's gravitational pull. So, even if we don't know what happens in the center of a black hole, next time you watch Star Trek, remember this: black holes aren't how they're portrayed in sci-fi. But now you know a little more about them.